Well, hello everyone. We're gonna talk about the topic of dynamic linear models or dynamic econometric models today, um, following the topic of stationarity that we had previous to this. And following the topic of DLM or dynamic linear models, we will have the autocorrelation topic because these two are very related. But we had to cover stationarity first because first thing to do when we are dealing with time series model, we need to make sure that whether we are dealing with non-stationary variables, and if we do, uh, what's the order of integration and what do we need to do to uh, make the right transformation so we have stationary variables in our model. As we said, if we use non-stationary variables, we will get completely misleading results from our regression model. But after we make sure that we are dealing with valid time series to use in these kind of linear models, um, we want to specify what lags or what variables at what point in time we should use in our model. If as opposed to dynamic model, we have a static model that in the static models they ignore the fact that any variable at the current point in time is related to some degree to same variable and its previous value in time, like a unit, 1 unit ago in time, that value is having a very high correlation uh, with the current value. So it's really not a wise idea to construct a model that doesn't include any lags. But dynamic models include lags, and that way uh, they have no assumptions against no information coming from previous points in time. Also, they allow it, and then you can see if you find significance or not. Which that would be basically what we want to talk about when we get to picking up the writer specification with in dynamic linear models. Some terminology here. Um, it's good to just like get familiar with this. You may not use it in practice at all, but it is something, especially when it comes to theory of time series. This is some kind of notation that you will see a lot, and that is this operator, the lag operator. So first order lag of xt is can be called L of xt. So this is not a number, or it's not multiplying this, or it's not an kind of like a function, but it's like an operator that if you use LXT, it's kind of same. It is the same way of using xt minus 1 x, that the variable x, the time series x, at t minus 1 point in time. And similarly, the pth order would be LP. Again, this is not L to the power of p or any thing similar to that you might have seen in algebra or calculus before, but this means just the pth lag of that variable. So the 0, 1 is basically itself. We're not going to have an operator for that. They also call this backshift operator, and sometimes show it by bxt. This is similar to lxt. We usually work with time in digitized unit, although the process could be completely continuous. For instance, say a price of a stock is, because it could happen at any minute in time, that price could go up and down in any second, especially today that you have all these applications that give you the power of real-time transactions. So, but if you want to analyze it, you need to pick a time. For instance, you may pick an hour, pick a minute, pick a second. Um, you could see some algorithms are working based on second base data. So the frequency of data is every second, and it could be in cryptocurrency, in stock market, and that's why some of these companies are fighting for the best internet speed, so they could get that advantage, tiny advantage in a second of time with their trading, basically decisions. But when again, it's no way out of it. You still gonna work with a discrete units of time. You could also argue for including leads in your model, but reality, you can't really justify it, because we don't know about that in future. But for some other studies, could be useful. But it's you don't see that in practice. Getting to the design of the dynamic regression models, we can um, generally show it in this form of this formula. So we will talk about what numbers these parameters like P, Q, and S could get, but in general, what we mean is that if we have a variable yt, and again, as a reminder, all of these variables should be stationary. If they're not, then we should not be at this stage. We should transform them and then get here. So assuming that all these are now stationary variables, we are talking about we have this yt, which is our dependent variable on the left-hand side, and we are including lags of the same variable on the right-hand side as well. So here we are including p lags of that variable. Now this p could be 1, so maybe there's just only one term in this uh, sigma, but maybe p is 6, so maybe you have 6 terms, 6 lags before including your model. Similarly, you start with including uh, the variables from the covariates in your time series analysis. For instance, x1, x2, or up to xk, and all of them are coming from t minus I time. The difference between these and the lags of the dependent variable is that in the dependent variable you cannot have yt minus 0. That's why the indexes start from 1, because that's what you're actually modeling. You cannot use it on the right hand side. Doesn't make sense at all. And but for your covariates, you could have the information of those variables on at the time that you are trying to predict y. So for them, you can start from I equals 0. For instance, y could be a reporting number, and that's maybe it's a quarterly data. Federal Reserve Bank is collecting data from all the banks to come out and then report the quarterly data, but that takes some time to consolidate all these information into that final report. So it may take about 45 days till you get information about that quarter. However, a lot of other information about that quarter is already happened. For instance, if you are looking at a interest rates or um, um, housing prices, stuff like that, those stuff are already observed in that quarter. So you can use those variables as your covariates, as your uh, independent variables in your model, but you cannot use that quarter's number as your right hand side because not reported yet. So that was an example of like how you can have an X that is happen at time t, but the Y hasn't happened yet. And of course, it's an example that you are looking at something like a quarterly base, or it's a you should have a relatively longer frequency, because the smaller the frequency is, these numbers are very close to each other. So um, it's hard to justify that. It's easy once you think about the concept behind this. It's also easy to memorize it. So it's not actually memorizing, it's just understanding. And then once you understand it, you can always recite it, because you have your dependent variable, you have max of your dependent variable, the necessary numbers, and that's our discussion here, to figure out what should be those necessary numbers, what should be the final specification. And then you have your right-hand side dependent variables as well as their, I'm sorry, right-hand side independent variables as well as their lags. Now, if you're having three right-hand side independent variables, you will have x1, x2, and x3, and then for one you might have 4 lags, for the other one 6 lags. So these numbers are going to be assigned accordingly. One other thing that we notice from this equation is that there is no interruption. So if you are including 6 lags, the lags from 0 to 5 are already there. We cannot just include the, for instance, fourth lag and don't have the first, second, and the third one. We will talk more about this, that why we do such thing. For instance, let's think about another example from Federal Reserve Bank. So if a federal funds rate, you want to model that, and then you find that federal funds rate today is very dependent to the interest rate spread 6 months ago. So interest rate spread in 5 months ago or 3 months ago is not that significant for you as much as the 6 months is. And you might want to look at the AIC and BIC and stuff like that and say, oh, that just support using the model with the 6 one, and then don't use the other lags. Well, when we had cross sectional data analysis, those variables are not related to each other. But when you have time series analysis, these lags are not just X, Y, and Z's, they are all from one family of time series. So they are all from the fund rate time series. So and if you don't use them, you're neglecting variable information that could actually explain, give more explanatory power to the spread variable that you're using on your right hand side. There is correlation between the lags in time series, because it's your YT is following your YT minus 1. That's the nature of it. And because of that, you also need to include those to these lags to bring that information, and don't make jumps like that. However, there is one exception to this that we will talk about. That is about seasonal lags that we will see in an example. So in order to specify a dynamic regression model, as we said, first thing we need to make sure that all the variables are stationary. So that's the first thing that we need to do. Let's, as we talk about these stuff, let's just start looking at it in an example too. So we want to open aggregate macro example 1, use aggregate AGG macro data. So here, that. So this has aggregate macro data from January 2001 to December 2010. So it has 10 years of data with monthly frequency, that gets us 120 observations. So let's read the data set. First, load the libraries that we're going to use. Read this data set, and we have these variables: consumer price index, household financial asset, total personal income, and unemployment. In this example, we want to use unemployment as our dependent variable. So we can imagine a model that unemployment is modeled by consumer price index, HAS, which is household financial asset, and INC, which is for income. Now, in this example, we are using, three lags of these variables, but so this is just not like those current values. This is conceptually just talking about this time series is modeled using these three time series. Now, but first thing that we have to do, we have to check whether we are fine with the non-stationary thing. So if you have non-stationary series, we need to convert them. Let's do that to get 4 tiles in our plot views, and then we plot CPI, HAS, INC. Oh, and read these guys. Now, visually, pretty obvious that they're non-stationary, but let's quickly do the intort on them. So we talked about this a bit, that the ADF test based on the augmented Dickey-Filler test, because they're using lags of the dependent variable on the right-hand side, they need to figure out how many lags is appropriate. They use AIC, BIC, maybe different measures to choose the best specification. So different packages could end up with different number of lags for their ADF. Thus, finally, they have a different results looking at the critical values and stuff like that. But most of the time, the inference is going to be the same. But we look at other stuff. We look at visual inspection, the rule of thumb for the standard deviation. That's the best, in my opinion, because it's computationally very cheap and it's very easy. But in this case, for instance, let's call ADF test. So by loading library T series, I can run this function ADF test for CPI, and I get this value. So it says alternative is stationary, so the null hypothesis is non-stationary. I get 37%. I fail to reject the null hypothesis, so it says that, oh, it's non-stationary. I clearly see it's non-stationary. Same thing here, that critical value is greater than these critical values, so we fail to reject the non-stationarity again. But maybe they are not. You see, this is minus 2.49, and that's a different number here. It's way larger than minus 2.49. But even that one is beating that 10%. So that wasn't as an example of difference between results of different packages. Now, same thing for HAS, that's going to happen. Now, for HAS, we got some problem with the specification to get the results here in for the ADF test, so that's where you can actually just go use the T-series package ADF test, and then again, you see that it's non-stationary. INC is non-stationary, unemployment is kind of non-stationary in this data, but it's worth mentioning that we are having what happens at towards the end, like in 2008, and that makes it a very severe case. So maybe if we didn't have the 2008 8 happening there, the case of non-stationarity was not this severe. Now, we need to transform the data, get it to a stationary form. So if we have um, positive values all throughout time for these variables, so there are always some stuff by nature that they are positive, we know that we can always do the log transformation. So here we are plotting the CPI with the log, and again the log is, as you see, is non-stationary, but we get the difference of the log. So now we have dCPI, DHIS, DINC, and DU as difference of the log. So they are the kind of showing the rate of growth, but in log form. And now if we plot those, we see that now the data look more stationary than what it was before. And our results for intward are also coming to be. So if I look at the previous one for change in CPI and look at it, I end up to have minus 7.04, which is very small, than even 1% is critical value. So it's stationary. Same thing for DHIS and DINC and DU. Now, if I want to bring so I said by 3 lags, I mean 3 lags in time. So we need to have 4 variables: the current variable and then 3 in previous time. I want to use that next, but as an example of including lags of our variables. But for that, so let's see where we are. We make sure that we are having stationary variables. And after that, we want to start with the general specification. That is, I'm not starting from just no lags and then include another lag and then add to the lags. I want to start from maximum number of lags and then narrow down to lower numbers if necessary. So that is going with general specification. Usually with macro data, maybe you include 2 years of worth of data for your lags. But if you have data with other frequency, let's say financial markets like a stock, a stock price, then that would be different. And maybe the stock price of 2 years ago is not like that informative about the price today, because the frequency of the stock market trade is way higher. So let's go and specify our general specification. We said our max number is 3, so we need to use this function in R that is called embed. What embed does, if you give it a time series, a vector, and then a number, it gives you new columns based on the number of lags that you decide. So if I want to create 3 lags in before, I need 1 column for the current one, and then 3 columns going for 1 unit in time before that, 2 units in time before that, and 3 units in time before that. So I'm looking at dCPI. It has 119 observation. Why 119? Because we take a difference once. So it was 120 originally at the level of that variable, and then once you difference it, would be 119 observations. Now I want to embed dCPI into LDCPI, and with p equal 4, and now if I look at LDCPI, Okay, LDCPI. Now, LDCPI is something that has four columns, not just one column. One, two, three, four. The first column is current, and then three lags in from previous times. So one other thing to point out here is that now we have 116 observations because we had 119 after we difference it. So from 120 goes to 119. Now from 119 goes to 116 because the first observation in that 119 doesn't have a first lag, doesn't have a second lag, and doesn't have a third lag. And the second observation has a first lag but doesn't have the second and third lag, and the third one has the first and the second but doesn't have the third lag. So what happens is that you kind of lose those three uh, observations. You only have them as lag variables here. So that's another three observation subtracted from 119, end up with 116. I can have, easy examples, like I can create something, call it vector, or like call it time vector, or no, time vector is 1 to 10. So if I want to look at time vector, if I want to use embed and do p equal 2, that is just like one lag. Now I have 9 observations because for first observations I should start from 2, having 1 coming as its first lag. You can play with this and then see how you can create different specifications. Of course, the limited number of observations you have, it's harder to more limited that number is, it's harder to use more lags because you're losing observations and the power of your model going to be lower. So we got here to use these things to create the lag variables, and now we want to start with our general specification. So this is our general specification. This is exactly what we had here. We want to transform this into something that R could understand. So I need my left-hand side variable, the lags of that, and then my right-hand side variables with its lags. And here we can see that I have my left-hand side variable, column 1 from LDU, that is like the lags of the unemployment difference. So that's the first one, and which is the current value, and then the previous values are coming from the second column, third column, and fourth column. And I do the same thing for my right-hand side variables, the DCPI, DHIS, and DINC, but I also include their current value. So I have 1, 2, 3, 4 for them rather than only just 2, 3, 4. And let's run that model. This is the summary of it. And you can see the results of the t-test here. Show the formula. We see that the second lag in time is for a change in unemployment is more significant than the others, and for DCPI we don't see much significance from the t-test results, and HIS we have some significant results, and then something at the 10% significance levels for INC. Now our next challenge is what do we need to do, what should we include on the right hand side. So this is get to part of choosing right hand side variables and the lag lengths. Well, a lot of times you can find a good design just because of the theory of the model that you're working with, and but other than that, from the stuff that we learned before, you can look at t-test values, your f-test values, you can use AIC and BIC, and along with the knowledge that you're bringing from the DGP and theory of the domain that you have, from your experience or from previous studies, then altogether you can come up with a good specification. Again, for all the stuff that you were checking before, you should check here too, maybe a little more, because of the tricky stuff just coming in because of time series analysis and stuff. And um, there are things that you need to pay attention more, but they're very similar to what we learned in the cross-sectional part of the linear regression, as the math part of these models are essentially the same. So naming some other techniques to choose between models is root mean square errors or root mean square prediction errors that you can use to compare performance of different models. One other thing is finally checking for serial correlation. As we said, it's the serial correlation or autocorrelation topic is very related to the DLM, and we will talk about that soon. As we pointed out earlier, we will have multicollinearity in time series most of the time because it's really hard to have a yt variable that is not following what yt1 was. There's some elasticity there. And similarly, the same thing happens with your x's. So when you are including different lags of your x's in your right-hand side, you will have that case of multicollinearity. But that would be the distribution, the motivation of for distributed lag models, which are including all those lags continuously in the right-hand side. So just again, going back to the discussion of if we figured out the fifth lag is the significant one, we don't want to just include that one. We include the fourth, third, two, and one as well to it potentially solves for part of this multicollinearity and also avoid to end up with having misleading results from your t-test. It's already really hard to trust those t-statistics, but if you mitigate that problem to some extent if you use all those lags. So for instance, in this example, just looking at the LDU, if I find the second lag in time was significant and the first one wasn't, I'm not gonna at the end final specification and not include that one. This is exactly what we were talking about when we were reviewing this example from federal funds rate. There's only one exception, as we pointed out, and that is including seasonal lags. If I want to include the price of something from 12 months ago, I don't need to include all the other 12 months in because right there I'm specifying some unique relationship that is coming from seasonal characteristics, not that evolution of the time series from a year ago completely to today. That way I needed to include all the other lags in between as well. We will talk about some example of that towards the end. So one thing that we use with choosing right-hand side variables in f-test, that's the from cross-sectional data we could have look at the combination of variables and see if that combination has any explanatory power on the left-hand side in our model. We use the same thing here, so we can look at the combination of all variables and all the lags of one variable in our right-hand side and compare that with a model that doesn't have that family of variables and those lags and see what would be the results of the f-test. If you find significant difference, then that means that those that family of variables is bringing good information to the table, but Otherwise, it's not relevant. So in time series, we have this concept of grandeur causality. Although it has the name causality, but it's we should mention that it's hard to. It's basically regression models are not designed to point at causality. They are merely there to show correlation. So in time series, what linear regression models are showing whether variables are correlated over time. Now, if we look at variable x, and by variable x, um, let's say, I mean, this could be this is matrix X that could have x1, x2, x3, so a family of different right-hand side variables that could have all their lags, and then we want to see whether these variables are affecting y. So for instance, let's talk two variables of just x and y here. And if x is having some relationship with y over time, and versus a model that we don't have x in it, if we run an f test between those two, we can uh, we can see that what would be the result. If the result is low p-value, that means we reject the null hypothesis that the variable x doesn't have any effect in explaining y. And if it has high p-value, then we fail to reject the null hypothesis that all variables or lags in variable x doesn't have any power in predicting or explaining y. So this is in essence the concept of grandeur causality. That is, you pick your variable, you run an F test for on the lags of that variable, and if you find significant results, you say that that variable grandeur causes Y. Otherwise, you don't find evidence for grandeur causality. So if you look at our general specification, if I want to see whether variable x1 is affecting yt, my null hypothesis would be all the coefficients related to x1, which would be beta 1, 0, beta 1, 1, all the way to beta 1, q, are jointly equal to 0. If I want to do the same thing with variable xk, now I need to run my f test for beta case. And similarly, if I wanted to run a grandeur causality test on the lags of the dependent variable itself, I need to run that test on 5 values for the number of dependent variables lags that I want to use in that test. So let's let's review what was happening in the ANOVA test. The ANOVA test is basically the F test that is calculating the residual sum of squares for the restricted and the unrestricted model, and then compare the difference to see whether you had any significance from the variables that were omitted. Now, let's look at an example of that here with the data set that we were working with. So in this case, I want to test for grandeur causality of consumer price index. So I had model 1 that included everything. I go create a model 2 that is basically model 1, but I don't have the consumer price index line in it. So all those stuff are out. So I only have this guy, that first line without the consumer price index ones, and then the following lines there. Now I can create model 2 and look at AIC and BIC. AIC and BIC already tell me that, so this is, if I look at AIC of model 1 is minus 521, and then AIC of model 2 is minus 529. So that is smaller. And then for BIC is 493, minus 493 to minus 475. Again, that is smaller. So both values are smaller. They both say that, hey, you don't need to include CPI. Why did I pick CPI? Because when I ran the summary of model 1, that one had the one that all the t-tests were not significant for CPI. So that was a good candidate to begin with. And now I got AIC, BIC telling me the same thing. I don't have to be worried about whether I have omitted variable bias, or because AIC and BIC gave me the same answer. Cancel each other's risk. Now, concept of grandeur causality to see whether CPI grandeur causes Y, are in this case, which is DU. So the thing is whether changes in consumer price index grandeur causes changes in unemployment. All the evidence so far is telling us no, but let's look at the ANOVA test, and we run that 94%. So we fail to reject the null hypothesis that all those lag values are jointly equal to 0 for CPI. That means that CPI changes does not grandeur causes unemployment changes. Now, another thing is checking for grandeur causality of household financial asset. I create another model, model 3, and here again, because I got rid of that CPI thing, I'm going to change my base model. I'm not going to have model 1 as my base model anymore. I'm going to have model 2. So I'm going to compare model 3 and model 2. So in model 3, I don't have the HAS, and look at AIC, BIC of model 3, and then look at that for model 2. We can see that for BIC model 2, BIC is larger, and for AIC, M3 for model 1 is M3 for model 3 is actually the AIC of it is larger than model 2. So model 2 says, AIC says model 2, BIC says model 3. Because model 3 has lower number of variables too. That's pretty, usual. So this is one of those cases that, the f-test definitely going to add more value. So we are running f-test. It's 2% p-value. So we reject that null hypothesis. So there is some information with having HAS in the model, so we want to include it. Now that we figured out that HAS, DU, and INC should be included in the model, and we can run the summary of M3 as well. This summary M3. And the summary, I have LDU not significant, but I'm including it in my model, and I have the second lag significant, but the third one is not. Then in INC, I have first one, second one, and third one significant. So actually should run model 2. Because that's the one that we pick based on the ANOVA test. So the third lag is not significant. I have first one, second one, and third one, but the in those columns. But so the current value, previous lag, second lag, and the third lag, but the third lag is not significant. And again, the third lag is not significant here too. So now I see that all those t-tests are not significant for those maximum number of lag that I chose. I can drop that one. That way I'm gaining at one more observation. Now I want to get better specification for that, and what I want to do is I go say, hey, P is 3, and then give me embed these guys again. So I gain that one observation relatively to what I had before, and now M4 is created. It's basically M2 but doesn't have the fourth lag. And I get the summary of M4. The summary of M4, and I look at it and I see that all the third columns are significant, and I'm including anything else in between. So that is how I want to use ANOVA test, which is in time series concept of grandeur causality, AIC, BIC, t-test, to come up with a good specification on my right hand side. There's one other thing to do in general with what we are doing here, and that is um, testing, finally testing for serial correlation, which will be the topic of um, next video. So, example of including a seasonal lag, we're gonna have this taste example of monthly ice cream sales. If we call that ST, sales of ice cream at time T, that is could be correlated with previous month or two, and also with sales of 12 months ago. So for instance, January 2020 sales could be very similar to January 2019 or July 2020 or July 2019. So we also want, so in that case, if we include the first two lags like previous month or two, and then the 12 months ago, we don't include the 11 months ago and other stuff to make sure that all those lags are included, because this is an exception to use one lag in before without including the previous lags of it, because it's a seasonal information. So if you want to develop this model, something more than just including sales of ice cream in previous couple months and then a year before, we can bring other information from from stuff that seems reasonable. So we added sales variables with the seasonal term of it. We also know that perhaps the price of ice cream uh, could 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 affect that. If I go to a store and then the price is lower than what I anticipated, I may buy a little more ice cream and then pack it in my freezer for next month, so I don't have to buy more ice cream with a higher price, probably based whatever I'm thinking. So or the other way around, maybe you find the price of ice cream right now is very high, so you won't buy at this point in time. So the price of ice cream at current point in time and previous point in time could affect the sales of ice cream at current point in time. That's why we you should perhaps include change in price of ice cream in uh, previous month or a month before that as well. And this is just simple model that we are creating based on intuition, and we haven't used uh, uh, any tools like AIC or BIC or anything like that to specify this. So if we want to show the model that we just talked about, it would be sales of ice cream with anticipation that the price of ice cream would be non-stationary with order of integration of 1. We need to take the difference of it. So we want to have the change of, we want to have the price of ice cream at time, at the previous time, so like current time minus last time, and then last period minus the period before that, that would be PT minus 1. And the sales from previous month, the month before that, and then 12 months before that. that would be an example of including seasonal lags there, and um, starting from some general specification that is supported by theory and intuition. But at the end of any models, we need to do this test, which is testing for autocorrelation. I just do it now for an example, and here we get a p-value. The p-value is high, so we don't have to worry about anything. If the p-value is low, that means that we have some case of autocorrelation, so our work is not done. And that would be the topic for our next video to wrap up basically the DLM and autocorrelation both together. Thank you, and see you next time.